After having evaluated the modal fields and propagation constants of the modes of a symmetric planar dielectric waveguide, now in this lecture let us find out how much power is associated with a mode, how much energy these modal fields carry as they propagate along the waveguide. So, we will do the analysis for TE modes, and this is the refractive index profile of the waveguide which we are talking about. And for this waveguide, this refractive index profile and propagation direction as z, the non-vanishing components of electric and magnetic field for TE modes are Ey, Hx and Hz. We know that the intensity of an EM wave is given by Poynting vector. So, we now need to find out what is the Poynting vector corresponding to these fields, the modal fields. The Poynting vector is given by S is equal to E cross H, and since we are talking about electromagnetic waves in optical frequency range, so E is fluctuating with a frequency of something like 10 to the power 15 hertz, and so the magnetic field, that is therefore S is also fluctuating at a very rapid rate. Any detector, even though it is very fast detector, cannot record such rapid fluctuations and so our eye. So, what we record is basically the average value, time averaged value. So, we will find out what is the average intensity by taking the average of E cross H, time average of E cross H. And since intensity is a real quantity, so while calculating intensity we must take the real parts of E and H. So, for TE modes I know that Ey is defined as Ey of x e to the power I omega t minus beta z. So, its real part would be Ey of x cosine omega t minus beta z. So, I have Ey, what is left is Hx and Hz, so that I can find out the Poynting vector and therefore the intensity. So, Ey is this. How do I find out corresponding Hx and Hz? Well, I know how H and E are related through Maxwell's equations. It is del cross E is equal to minus mu naught del H over del T. So, if I expand this in matrix form, it would look like this, and in E I know Ex is equal to 0 and Ez is equal to 0, only Ey is non-vanishing for TE modes. So, from here I can find out what is Hx, Hy and Hz. Okay. Hy is not there of course in case of TE mode. So, Hx and Hz I can get from here. So, from here I get, if I take the x component, del Ey over del z is equal to, with a negative sign, is equal to minus mu naught del Hx over del t, and Ey is given by this gives me del Hx over del t is equal to beta over mu naught Ey sin omega t minus beta z. If I integrate this, I can get Hx, integrate this with respect to time. So, I get Hx is equal to minus beta over omega mu naught Ey cosine of omega t minus beta z. Similarly, if I take z component from here, then I get del Ey over del x is equal to minus mu naught del Hz over del t, and if I differentiate this with respect to x, I get del Hz over del t is equal to minus 1 over mu naught dEy over dx cosine omega t minus beta z. Integrating it over time will give me Hz, which comes out to be minus 1 over omega mu naught d Ey over dx sin omega t minus beta z. So, I have all the three components in place corresponding to TE modes. So, now we are ready to calculate the Poynting vector. Poynting vector is given as E cross H. So, I fill in the values here now. So, Sx, Sy, Sz in matrix form, I can write it like this. These are the non-vanishing components of electric and magnetic fields for TE modes Ey, Hx and Hz, and from here I can find out what is Sx, Sy and Sz, that is x, y and z components of the Poynting vector. From here I get Sx is equal to Ey Hz minus 0. So, average value of Sx would be average value of Ey Hz, and if I put Ey Hz as I had calculated in the previous slide. So, this comes out to be like this, and in this what I see a factor here cosine omega t minus beta z multiplied by sine omega t minus beta z. Okay. So, this is something like half of sine 2 omega t minus 2 beta z. So, this is fluctuating, okay, and if I average it over a complete cycle for any value of z, the average value would be 0, the time average would be 0. So, this gives me 0. So, x component of Poynting vector, the average value of x component of Poynting vector comes out to be 0. Now, let me evaluate Sy. Sy is clearly 0 from here itself, and Sz, if I calculate Sz will give you minus Ey Hx, minus Ey Hx. So, now I substitute for Ey and Hx. So, I get beta over omega mu naught E square of x cosine square omega t minus beta z. I know for any value of z, the time average of cosine square omega t would be equal to half. So, this gives me beta over 2 omega mu naught Ey square of x. So, what do I see? I see that for TE modes, the average value of Sx and Sy is 0, and I get the average value of only z component, and this is obvious also, this is understandable, right, because my mode is propagating in z direction. So, it should carry energy along z direction. So, this is the intensity. So, if I know the modal field, that is Ey of x, then I can find out the intensity. If I integrate it over the entire area, then I can get the power associated with the mode. So, intensity is this. Okay. To find out power, I should integrate it over the area, over the transverse cross section. The mode is propagating in z direction. So, the transverse plane is xy plane, but y is also extended to infinity. So, I cannot integrate it over y, I can integrate it only over x. So, in the case of planar waveguide, I cannot have power in terms of watts, but I can have only power per unit length in y direction, because I can integrate it only over x. So, I get P is equal to beta over 2 omega mu naught integration Ey square x dx from minus infinity to plus infinity, and this will give me power per unit length in y direction in the units of watts per meter. So, now if I know Ey of x in the entire region, I can find this out. So, let us consider the case of symmetric modes to evaluate this. The modal field for symmetric modes is given by a cosine kappa x for mod x less than d by 2 and c to the power minus gamma mod x for mod x greater than d by 2. So, let me substitute this into this expression. So, I get, and I also make use of the fact that this is symmetric mode. So, this integral from minus infinity to plus infinity can be written as 2 times 0 to infinity. So, I make use of that and then substitute E y of x, then I get beta over 2 omega mu naught 2 times 0 to d by 2 a square cosine square kappa x dx plus d by 2 to infinity c square e to the power minus 2 gamma x dx. So, let me evaluate this integral while using the boundary conditions also, because I need to relate c to a. So, here I simplify this as I take a square outside and cosine square kappa x can be written as 1 plus cosine 2 kappa x by 2 and this c square comes out, so c square over a square integral d by 2 to infinity e to the power minus 2 gamma x dx. And since from boundary conditions I know a cosine kappa d by 2 would be equal to c times e to the power minus gamma d by 2. So, from here I will get c over a, which I substitute here and evaluate this integral, which is very simple, e to the power minus 2 gamma x divided by minus 2 gamma, and then I put the limits. So, when I simplify this, what I get d by 2 from here and sine kappa d over 2 kappa from here and 1 over gamma cosine square kappa d by 2 from this term. This I can further simplify. So, I take this factor 2 outside. So, this becomes d and this becomes 2 over gamma cosine square kappa d by 2 can be written as 1 minus sine square kappa d by 2. So, this 2 over gamma which is associated with 1 comes out here and the rest of the terms I can write as sine kappa d as 2 cosine kappa d by 2 sine kappa d by 2 and this I take common. So, in the bracket inside I will be left with a term which goes as gamma minus kappa tan kappa d by 2. It would be clear if you do this little mathematics. And why I have done in this fashion, because I can see this is nothing but the transcendental equation. Okay. So, this has to be 0 because gamma is equal to kappa tan kappa d by 2. So, if this is 0, this whole thing goes out and I get a very neat expression for power associated with the symmetric modes, and it comes out to be beta over 2 omega mu naught half a square times d plus 2 over gamma. I can remember it in a very interesting way, and it is interesting to see that this term comes out to be the area of triangle under this curve. So, how? You see that P is equal to beta over 2 omega mu naught times integral E y square of x dx. So, P is beta over 2 omega mu naught integral minus infinity to plus infinity E y square of x dx. So, if I find out the area under this E y square of curve, then let us see what do I get. So, if this is E y square as a function of x, then this is nothing but a square, this is waveguide width, and field extends into N2 region by distance 1 over gamma on either side. So, if I make a triangle which has height a square and base as d plus 2 over gamma, then the area of this triangle is simply half a square times d plus 2 over gamma. So, this is interesting that this comes out to be like this. For TM modes, I can do the same analysis and find out the power associated with TM modes, and it is given by this. Although I had found out the power by taking the example of symmetric modes, this expression and this expression, these expressions are valid for anti-symmetric modes also. Okay. This can be proved and this can be evaluated. So, this is how I can get power associated with a mode, and these powers are in watts per meter, power per unit length in y direction. Let us work out some examples. This is the example adapted from Introduction to Fiber Optics by Ghatak and Tyagarajan, where I have a planar symmetric waveguide with N1 is equal to 1.5, N2 is equal to 1.48 and D is equal to 3.912 micrometer. At lambda naught is equal to 1 micrometer, beta for TE0 mode is this and beta for TE1 mode is this. It supports two modes at 1 micrometer wavelength. If at Z is equal to 0, the electric field in the guiding film is given by this. So, you see I have TE0 mode and TE1 mode, and at Z is equal to 0 I excite both the modes with different amplitudes. This mode is excited with this amplitude, TE0 mode is excited with this amplitude and TE1 mode is excited with this amplitude. Okay. So, the field, total field at Z is equal to 0 is this much volts per meter. Then what is the power carried by each mode? You can take mu naught is equal to this. So, I know the power carried by a mode is given by this. So, what I need to know? I need to know what is the beta for that mode, what is the amplitude of that mode, what is gamma for that mode, and of course, I need to know what is omega, and omega is nothing but 2 pi c over lambda naught. Since lambda naught is given to you, so you can immediately calculate the value of omega. Then you find out gamma, beta is already given to you, A is already given to you. Gamma you can find out from square root of beta square minus k naught square n2 square. So, for TE0 mode, this gamma comes out to be 1.4126 micrometer inverse. For TE1 mode, gamma comes out to be 0.9979 micrometer inverse. And if you put these values into this expression, you will find that for TE0 mode, the power associated comes out to be 1 watt per meter, and for TE1 mode also you find out that the power comes out to be 1 watt per meter. In fact, these amplitudes have been adjusted in such a way that both the modes carry unity power. When the amplitudes are adjusted in such a way, then they are power normalized. You remember that when we found out the modal fields, we had retained A only and we related C to A and said that A can be found out by normalization. This is one way of normalization, that you find out the value of A in such a way that the modal field carries unity power. So, these are power normalized modes. let me take another interesting example of again a symmetric planar waveguide which supports two modes TE0 and TE1. Their propagation constants are beta 0 and beta 1 and electric field amplitudes are A0 and A1. If the difference in their propagation constants is defined by delta beta and Z is the direction of propagation, then what would be the total intensity in the guiding film at different values of Z? First one at Z is equal to 0, second Z is equal to pi over delta beta, and third Z is equal to 2 pi over delta beta. So, what do I see here? At Z is equal to 0, the total field would be A0 cosine kappa 0 x, where kappa 0 you can find from beta 0, plus A1 sine kappa 1 x, where kappa 1 can be found out from beta 1. So, at Z is equal to 0, this would be the total field. As these fields propagate, it will go with propagation constant e to the power I beta 0 z, this will go as e to the power I beta 1 z. So, as they propagate in z direction, there would be a phase shift accumulated between them, a phase difference accumulated between them, and that phase difference would be delta beta z. So, you will have e to the power I delta beta z, and I know that at z is equal to pi over delta beta, if z is equal to pi over delta beta, then this e to the power I delta beta z would simply be e to the power I pi, e to the power I pi, which means that these two modes would be pi out of phase, and if we are doing in the way e to the power I omega t plus, then it should be minus. So, we can have this form of expression. So, instead of plus I beta z, because I am doing it in such fashion, so I can retain the same convention. So, the thing is that the two modal fields will be pi out of phase when they traverse this distance. Okay. The intensity is nothing but the field square. So, intensity would be some alpha times Ey square. So, this would be at z is equal to 0, but at z is equal to pi over delta beta, the total field would be this minus this because they are pi out of phase. So, the intensity would be this much, while at z is equal to 2 pi over delta beta, it would be 2 pi phase shifted. 2 pi phase shifted means there is no phase shift. So, your intensity would again be this. And the analysis of guided modes of a planar symmetric waveguide with food for thought. I had said that in a symmetric planar waveguide, the guided modes are the superposition of plane waves making angles plus minus theta m from the waveguide axis, where the angles are given by cos theta m is equal to beta m over k naught n 1. So, if I launch two plane waves at angles plus minus theta 0, then I excite the T0 mode, then T0 mode is excited and the pattern corresponding to T0 mode is formed and it goes along the waveguide and it sustains its shape. Similarly, if I excite at plus minus theta 1, T1 mode is there. The question is, what happens if the waves are launched at angles which do not correspond to these guided modes, the angles corresponding to these guided modes. Please think about it. And in the end, I complete this analysis of planar symmetric waveguide by briefly mentioning the radiation modes. I have seen that if beta lies between k naught n2 and k naught n1, or n effective lies between n2 and n1, then I have guided modes. If beta is less than k naught n2, this should be less than n2. So, n effective is less than n2 or beta is less than k naught n2, then what will happen? If I write down the equation, wave equation for TE modes, and then I write it down in both the regions, in this region and in this region, then for mod x less than d by 2, I have this equation, beta is less than k naught n2 and hence beta is also less than k naught n1. So, kappa square is positive. Now, in the region for mod x greater than d by 2, I would have d2 ey over dx square plus k naught square n2 square minus beta square ey is equal to 0. And since beta is smaller than k naught n2, then if I define this as delta square, then delta square would be positive. And what I will have? I will have oscillatory solutions here as well as here. So, everywhere I will have oscillatory solutions, which means that energy is carried up to infinity in x direction, that is energy radiates out in the n2 region, and these kind of modes are known as radiation modes because the energy radiates out corresponding to these modes, and they form continuum. Okay, they are not discrete modes, so they form continuum of modes. So with this I finished the analysis of planar waveguide, symmetric planar waveguide. The whatever we have learned about the modes, modal fields, and the procedure of finding out the modes would be very useful when we will do a more complicated structure such as optical fiber. Thank you.